Imagine, if you will, a universe governed not by a multitude of complex laws, but by a single, elegant whisper. A solitary principle so profound, so all-encompassing, that it orchestrates the dance of galaxies, the arc of a throne ball, and even the subtle shimmer of light across a pond. For centuries, humanity has sought this master key, this unifying truth that could unlock the deepest secrets of existence. Today, our journey begins, not with grand pronouncements, but with a simple challenge, a seemingly innocent puzzle that would ignite a revolution in thought. Our story opens in the late 17th century, a time when the world was still reeling from the genius of Isaac Newton, whose laws of motion had seemingly charted the cosmos. Yet, there were minds restless for more, for deeper symmetries. One such mind belonged to a brilliant mathematician, a man we shall call John Bernard. He posed a problem so captivating, so deceptively simple, that it would draw the attention of the brightest intellects across Europe. Picture this. You have a bead and you want it to slide down a wire from one point to another, under the sole influence of gravity. The catch? You want it to reach the destination in the absolute shortest time possible. What shape should that wire take? Should it be a straight line, a gentle curve, or something else entirely? This was John Bernard's famous Brachis-Dekron problem, the challenge of finding the curve of fastest descent. It was a gauntlet thrown, an intellectual duel. And among those who accepted the challenge, one figure stands above all others, the legendary Isaac Newton himself. It is said that Newton, upon receiving the problem, solved it overnight, after a long day's work. His solution, published anonymously, was correct, a testament to his unparalleled genius. Yet, John Bernard's own path to the solution, though perhaps taking a little longer, was considered by many to be more profoundly creative, more insightful. For Bernard didn't just solve the problem. He saw a deeper connection, a hidden thread weaving through different domains of physics. Bernard's genius lay in his ability to look beyond the immediate mechanical problem and draw inspiration from an ancient, almost mystical principle. He reached back across millennia to the wisdom of Hero of Alexandria, a brilliant mind from antiquity who observed something remarkable about light. Hero proposed that when light reflects off a mirror, it always chooses the path that minimizes the distance traveled. This idea, deceptively simple, carried a profound implication. Nature, even then, seemed to operate with an inherent sense of efficiency, of economy. Centuries later, in the mid-17th century, another brilliant mind, Peter Farmer, refined this concept. Farmer's principles stated that light, when traveling from one point to another, always takes the path of least time. Not necessarily the shortest distance, but the quickest journey. This principle elegantly explains Snell's law of refraction, why light bends when it passes from air into water. It's not because it knows where it's going, but because its path is a continuous, instantaneous optimization, constantly seeking the fastest route through varying mediums. Imagine a lifeguard on a beach, trying to reach a drowning swimmer in the water. They wouldn't run a straight line to the swimmer, because running on sand is faster than swimming in water. They'd run further along the beach, then swim a shorter distance, optimizing their overall time. Light does something similar, but with far greater precision. John Bernard, wrestling with his Brachis-Dekron problem, saw this connection. He had a mechanical problem, a bead sliding down a curve. But what if he could transform it into an optical one? What if he could imagine light passing through layers of varying density, where the speed of the light corresponded to the speed of the bead? In this ingenious conceptual leap, he realized that the mechanical problem of the fastest descent was analogous to light seeking the path of least time through a medium where its speed changed with height. With this brilliant insight, he deduced that the curve of fastest descent was not a straight line, nor a simple arc, but a cycloid, the same path traced by a point on the rim of a rolling wheel. It was a stunning revelation, a testament to the interconnectedness of nature's laws. This idea, that nature seeks to minimize something, was a powerful undercurrent, a whisper growing louder. But what exactly was it minimizing? And could this principle extend beyond light and simple mechanical problems? Roughly 40 years after Barnard's triumph, a bold and ambitious thinker named Peter Lewis stepped forward. He proposed a revolutionary new quantity, something he called action. He defined it, in simple terms, as the product of an object's mass, its velocity, and the distance it travels. Peter Lewis declared, with unwavering conviction, that nature always strives to minimize this action. This was a monumental claim, a single, overarching principle governing all motion, from the smallest particle to the grandest celestial body. 2. It was a breathtaking assertion, but it was also met with fierce resistance, even ridicule. Peter Lewis was a brilliant, but often controversial figure, and his proposal, while visionary, initially lacked the rigorous mathematical foundation and clear physical reasoning that his contemporaries demanded. He was attacked, his ideas dismissed as vague and unproven. Imagine standing alone, with a profound insight, only to be met with skepticism and scorn from the scientific establishment. It takes immense courage, immense belief, to press on. Fortunately, Peter Lewis was not entirely alone. He found a formidable champion in the towering intellect of Leo Euler, one of the greatest mathematicians of all time. Euler, recognizing the profound potential of Lewis's idea, rose to its defense. He understood that Lewis had glimpsed a fundamental truth, even if the initial formulation was incomplete. Euler took Lewis's concept of summing up mass times velocity times distance and, with his unparalleled mathematical prowess, transformed it. He replaced the clumsy sum with the elegant precision of an integral, a continuous summation over time. 4. Importantly, Euler didn't just refine the mathematics. He found the conditions under which this principle held true. He demonstrated that for this principle of least action to be valid, certain fundamental conservation laws had to be in play, specifically, the conservation of energy. Euler's work provided the much-needed mathematical rigor, elevating Peter Lewis's bold hypothesis from a speculative idea to a robust scientific principle. It was a beautiful collaboration across minds, one providing the audacious vision, the other, the meticulous framework. Its stage was now set for the next great leap. It came from another mathematical titan, Joseph Lane. Building on the work of Euler, Joseph Lane provided a general proof for the principle of least action, solidifying its place as a cornerstone of physics. To do this, he had to invent an entirely new branch of mathematics, the calculus of variations. This powerful new tool allowed mathematicians to find functions, or curves, that minimize or maximize certain integrals, precisely what was needed to find the path of least action. Joseph Lane's work was a triumph of abstraction, demonstrating that this principle wasn't just a clever trick for specific problems, but a universal law, applicable to any physical system. He showed that if a system followed this path of stationary action, it would inherently obey the laws of motion. From a simple bead sliding down a wire, through the ancient wisdom of light, to the audacious claims of action, and finally to the rigorous mathematical proofs of Euler and Lane, we have witnessed the birth of an extraordinary idea. A principle that suggests nature, in its infinite complexity, operates with an underlying simplicity, always choosing the most economical, most efficient path. But we have only just begun to scratch the surface of its power. We've seen the historical roots, the initial struggles, and the mathematical foundations. The full, modern formulation of this principle, its breathtaking equivalence to Newton's laws, and its astonishing ability to describe everything from the reflection of light to the intricate dance of planets, even hinting at the quantum realm. That, my friends, is a story for our next chapter. For now, let the whisper of this single rule resonate in your mind. a prelude to the profound elegance that awaits. Thanks for watching, and be sure to subscribe for part 2. We stand at the threshold of a revelation. For centuries, the greatest minds in physics Fermat, Bernoulli, Maupertuis, Euler, Lagrange contributed a vital piece to a grand puzzle. But it took one true visionary to weave these threads together into a masterpiece that describes the universe. William Rowan Hamilton. Imagine. The year is 1834. Science, for all its progress, was still wrestling with the complexities of motion. Newton's laws were powerful, yes, but applying them to intricate systems was like untangling a knotted web of forces and coordinates. It was into this landscape that Hamilton stepped, not to replace Newton, but to elevate physics to a new plane of conceptual beauty. Hamilton, a brilliant Irish mathematician, took the concept of action and gave it a rigorous, undeniable form. He redefined it as an integral over time of a new, profound quantity. The Lagrangian. And what is this Lagrangian? It's simply the difference between a system's kinetic energy and its potential energy. Kinetic minus potential. From this elegant subtraction emerges the very fabric of how things move. Hamilton's principle states that a physical system, in getting from one point to another, will always follow a path where this action is stationary. It doesn't always have to be a minimum, but it's a point where the action doesn't change for small wiggles in the path. This insight was nothing short of revolutionary. Think about the sheer audacity of this idea. Instead of calculating all the forces acting on an object at every single moment, Hamilton proposed something different. He suggested that nature, at a fundamental level, doesn't care about all the pushes and pulls. Instead, nature simply seeks out the path that makes this one single quantity, the action, stationary. It's like a grand cosmic optimization problem. And the universe is the ultimate solver. This wasn't just a clever math trick. It was a profound shift in perspective. Newton's laws tell us how things move when forces act on them. Hamilton's principle tells us why they move that way, because that path is the one of stationary action. It's almost as if nature has a goal, a preferred route. And this preferred route, this path of stationary action, is precisely what gives rise to Newton's second law, F equals ma. Yes, you heard that right. The entire foundation of classical mechanics can be derived from this single, elegant principle. Imagine the power of this. From one simple, universal rule, we can derive the motion of a falling apple, the swing of a pendulum, the orbit of a planet, the trajectory of a bullet, the bounce of a ball. All of it emerging from a single, unifying concept. It's like finding a master key that unlocks every door in a vast, complex castle. But the true genius of Hamilton's Lagrangian method is its practical power. Think about solving a problem with Newton's F equals ma. A simple object moving in a straight line is easy. But what about a double pendulum? Two pendulums attached to each other. Its motion is incredibly complex, chaotic even. Trying to track all the forces and components becomes an algebraic nightmare. This is where the Lagrangian shines. You don't need to worry about the internal forces or the tension in the rods. You just define the kinetic and potential energy of the system. Express them in terms of more natural coordinates, like the angles of the pendulums. Calculate the Lagrangian and apply the Euler-Lagrangian equations. Suddenly, a seemingly impossible problem becomes manageable, even elegant. The complexity just melts away. Death. This is the profound advantage. The Lagrangian method lets us choose the most natural coordinate system for any problem. Whether it's spherical coordinates for planets or angular coordinates for pendulums, the principle is the same. It frees us from the tyranny of forces and lets us focus on the more fundamental quantities of energy. It's a testament to the human mind's capacity for abstraction. We started with a physical observational bead sliding down a curve and through a journey of analogy. intuition, and rigorous math, we arrived at a principle so powerful, it describes the very essence of motion. Now, a crucial clarification. While it's often called the principle of least action, a more accurate name is the principle of stationary action. Why the difference? Because the path nature takes isn't always the absolute minimum. Sometimes it's a local maximum, or even a saddle point to point where the action is stationary, meaning its rate of change is zero for small deviations. Imagine you're in a mountain range looking for a path with the least elevation change. Most of the time, you'll find valleys. But sometimes, a path over a ridge or through a pass is also a stationary point, even if it's not the lowest possible route. The universe is choosing a path where any slight deviation would increase the action. It's a subtle but important distinction that reflects the sophisticated math at play. So, we've seen how this one principle unifies all of classical mechanics, offering a superior framework for understanding and predicting motion. It simplifies the complex and reveals the hidden order. But the story of action doesn't end here. Its journey continues, venturing into realms that would have been unimaginable to Hamilton. The concept of action would prove to be a crucial harbinger of the revolution that was to come, the quantum revolution. As the 19th century gave way to the 20th, physicists found things that classical mechanics simply could not explain. The universe, at its smallest scales, behaved in truly bizarre ways. One puzzle was the ultraviolet catastrophe, where classical physics wrongly predicted that a hot object should emit infinite energy. It was a crisis. It was here that the concept of action resurfaced, not as a continuous quantity to be minimized, but as a fundamental quantized unit. Max Planck, trying to solve the ultraviolet catastrophe, proposed that energy comes in discrete packets, or quanta. The size of these packets was proportional to their frequency, with the constant of proportionality being h. Planck's constant, T. And what is Planck's constant? It is, in essence, a unit of action. A tiny, irreducible packet of action. This was the birth of quantum theory. Suddenly, action wasn't just a mathematical tool for describing paths. It became a fundamental quantized ingredient of reality itself. This revelation was staggering. The very principle that described the grand ballet of planets was also, in its most fundamental form, woven into the fabric of the subatomic world. The principle of stationary action wasn't just a clever way to do physics, it was a deep truth about the universe, spanning the macroscopic and the microscopic, the classical and the quantum. We are now on the precipice of the quantum realm, where Hamilton's principle takes on an even more mystical, philosophical dimension. The idea that nature chooses a path takes on new meaning. When we consider particles that seem to explore all possible paths at once, the journey from a rolling ball to the fundamental nature of reality, all guided by this one simple idea, is one of the most inspiring sagas in science. It reminds us that the most profound truths are often hidden in the simplest of observations. As we prepare to dive into the quantum implications, remember the thread that connects Hero's light, Bernoulli's curve, Hamilton's equations, and Planck's quanta. It is the thread of action, a testament to the universe's elegance. In the next chapter, we'll plunge into the heart of quantum mechanics, where this principle takes on its most mind-bending form, revealing a universe far stranger and more beautiful than we could have ever imagined. Thanks for watching, and don't forget to subscribe for the next part of this incredible journey. Prepare to have your perception of reality profoundly expanded. We stand at the threshold of the quantum realm, where the principle of stationary action takes on its most mind-bending form. We've traced it from ancient Greeks pondering light to 19th century mathematicians describing the dance of planets. Now, we confront its relevance to the very building blocks of existence. Remember, the classical world, governed by Newton's laws, seemed to dictate a single, deterministic path. The principle of least action offered a deeper perspective. Nature chooses the path that minimizes a quantity called action. But in the quantum world, this idea undergoes a magnificent transformation. Here, particles don't just choose a path, they explore all possible paths simultaneously. This radical idea was born from a crisis in physics. One glaring issue was the ultraviolet catastrophe. Classical physics predicted that a hot object, like a light bulb filament, should emit an infinite amount of energy at short wavelengths. Clearly, this wasn't happening. Light bulbs don't explode with infinite energy. It was Max Planck who, in a moment he called an act of despair, proposed a solution that changed everything. He suggested energy wasn't continuous, but came in discrete packets, or quanta. He found that the energy of these quanta was proportional to their frequency, with the proportionality constant now famously known as Planck's constant, h. And what did Planck's constant represent? It was a fundamental unit of action. Yes, the very same action from our previous discussions. Planck discovered that at the subatomic level, action itself is quantized. It comes in whole number multiples of this tiny, fundamental unit, h. This was the birth of quantum theory, and the principle of action was at its very heart.